you ever wondered why drinking soda doesn't immediately make your blood acidic? Or why shampoos and skincare products don't irritate your skin despite containing various chemicals? The secret lies in something called a buffer. In this lesson, we'll explore what a buffer is, how buffering capacity works, and provide a simple example of it to make it all clear. Let's get started. First, let's define what a buffer is. A buffer is a solution that resists changes in pH when small amount of an acid or base are added. It helps maintain a stable pH, which is crucial in biological, chemical, and industrial processes. Buffers are composed of a weak acid and its conjugate base. Example, acetic acid and acetate. Second, a weak base is a weak base and its conjugate acid. Example, ammonia and ammonia. These components work together to neutralize any added acid or base, keeping the pH stable. Buffers are essential in many aspects of life. Let's take a look at a few examples where they play an important role. First, in the human body, our blood has a buffer system called the carbonic acid and bicarbonate, which help maintain a stable pH between 7.35 and 7.45. This stability is crucial because even small changes in pH can be harmful to our body. Second, in everyday products, such as shampoos and skincare products, contain buffers to prevent irritation. Without them, these products could become too acidic or too basic, damaging skin and hair. Now that we understand buffer, let's talk about buffering capacity. This refers to how much acid or base a buffer can handle before its pH starts to change significantly. Buffering capacity is the ability of a buffer solution to resist changes in pH when an acid or base is added. It depends on, first, the concentration of buffer components. Higher concentration is equal to stronger buffering capacity. Second, the ratio of acid to conjugate base or base to conjugate acid. A high buffering capacity means a buffer can absorb more acid or base before its pH starts to change significantly.
In this video, we're going to demonstrate the ability of a buffer to resist changes in pH when strong acid or base is added, and talk about and calculate buffer capacity. What we have here are two solutions with equal pHs, approximately 4.7. On the right, we have a simple, strong acid solution of HCl at a concentration of 1.7 times 10 to the negative 5 molar, which, if you take the negative base 10 logarithm of that, comes out to a pH of 4.7. We have 250 milliliters of that, and we also have 250 milliliters of a buffer solution on the left-hand side that contains acetic acid as well as sodium acetate. And we've adjusted the amounts of the acid and its conjugate base such that the pH is again 4.7. We also have 0.1 molar sodium hydroxide solution as well as methyl red indicator, which is going to show us visually what happens to the pH as we add a strong base. So we'll add methyl red indicator to both of these solutions and stir a little bit to give the solutions some color. And next what we're going to do is add equal volumes of the 0.1 molar sodium hydroxide solution to each beaker. Sodium hydroxide is a strong base, so the pH of the solutions should go up. We add 10 drops of that solution to the right-hand hydrochloric acid solution, which is approximately half a milliliter, and we add that same number of drops to the buffer solution on the left. After stirring, we see that the indicator changes color in the HCl solution, but remains red in the buffer solution, and the pH readings in the two solutions indicate that the pH has increased drastically in the HCl solution, approaching 9.9, while the pH has remained at 4.7 in the buffer solution. So the buffer solution has resisted a change in pH, thanks to the ability of the acetic acid to react with the added strong base.